Hello everyone, welcome back. So as you can see, we have lots of circles rotating today. So we will be discussing some angle properties of circle. Now before we move on to angle properties, let's review some important concepts related to circle. So let's recall, if you have a circle, this point in the middle is called center. If you join the center with the boundary, we call it radius. Double of radius is called diameter, and if you go around the circle, this boundary is called its circumference, right? Now moving further, if we look at the inside area, the total area is pi r squared and circumference is 2 pi r, where r is the radius of the circle. Have a look at another circle whose center is given. So if you join the center with the boundary, this is radius, this is another radius. So when you join two radius, there is an angle between these two radii. So if this angle is theta, then this part of the circumference is called arc. Now since it is a smaller arc, so we call it minor arc. And also the bigger part of the circumference is also called an arc. Since it is bigger in size, so we call it major arc. So major and minor arc can be anywhere. Now, if you look at this shaded part, this is called sector of the circle, and area of the sector is, and since this is smaller in size, we call it minor sector. So the above this, the bigger part is called major sector. Length of arc, since the arc is part of circumference, so we find only its length. We do not find its area. So length of arc is, we go with the proportionality rule. So when the total angle is 360 degree, length of arc, that is the circumference, is 2 pi r. So when the angle is theta, this is theta over 360 of 2 pi r. And when it comes to area of sectors, similarly, we use the proportionality rule, and it is theta over 360 times pi r squared, right? Moving on, this theta is called, either we call it central angle or we call it degree measure of this arc. We also call it central angle, right? Okay, the next we are going to review is if there is a circle, this is this line that joins 2 points on the circumference is called a chord. And if you see, the diameter will also be a chord, and diameter is the biggest chord in a circle. A chord divides circle into two parts. These two parts are called segments. So on the lower side, which is smaller in size, we call it minor segment, and the upper one is called the major segment. Again, if they both are equal, we call them semicircles. Angle made in the segment, uh, there are certain angles we say they are made in a segment. So how do we identify whether an angle is made in a segment or it is just an angle? So an angle in segment starts at one end of the circle, or say one end of the chord, goes up to the circumference and ends at another end of the chord. For example, if this is a circle, if you look at this angle, this is the chord. It starts from here, goes up to circumference, then back to the other end of the chord. So this is an angle made in the segment. If you look at this angle, it starts from here, it ends here, but it doesn't go up to the circumference. Similarly, another angle starts from a point inside the circle, goes up to circumference and end at the chord. This is also not an angle made in the chord. So these and the segment. So these two are not angles made in the segment, but this is the angle made in the segment. Okay, remember this thing. Also, if you recall, alternate segment. What is an alternate segment? Let's say this is your circle, and here is your segment. If you are working in this segment, then the other segment is called alternate segment. So if you are working in the lower segment, the upper segment is called alternate segment, and if you are working in upper segment, the lower segment will be your alternate segment. right? Moving on, if there is a point on the circle and if you draw a line touching that point, we call it a tangent. Clear? This is called a tangent. Also recall, if you have a circle like this, then this angle that is made at the center, is called angle subtended at the center. And if there is an angle that is made at the circumference, we call it something like this. We call it angle subtended at the circumference, right? So with these reviews, let's start and explore what happens when you draw angles within a circle. So we will explore it with the help of a graphic calculator, and I'll be using Texas Instruments TI-Nspire CX II calculator, and we'll see how different angles are related, what are the properties, geometric properties, let's say, of a circle. So let's start. Here is your calculator. So first thing what I'll do is I will open a new page. So I'll open a new geometry page here. In new geometry page, I'll draw a circle. So I'll go to menu, go to shape, and draw a circle. To draw a circle, just click anywhere and just extend your cursor out. So this is a circle. Now I would like to draw some angles here and some chords, all those stuffs. So I'll just select, go to point and line. I'll select a segment. I'll start from here. There is a segment. This is another segment. This is another segment. This is another segment. To start with, let's explore the first angle property. Now, if you see out here, point A, B, and C, these are dynamic points. Dynamic points means we can move these points, and say point C can be moved, point A can be moved, so is point B. So we can move all these 3 points. Now, these 3 points are moved. These angles which are made, they will also change. So how these angles change? First, we are going to explore these, and we'll come up with a conjecture and then with a theorem. So let's start. So first we measure these angles. So for this, go to measurement, angle. Our first angle is this. So I'll measure this angle, and the second angle I'm going to measure is here. So I'll measure this angle. Now it shows in radian, so simplified, I'll convert it to degree. So these are my angles, 99.02 and 49.05. So if in first glance, we can see that this angle is 2 times that angle. But if we move, we cannot, this is our conjecture, but we cannot generalize it on the basis of one value. So what do? We move this point A. So when you move this point A, you see these angles are changing. So when these angles change, what happens? For example, this one, if I make 120.5, top angle is half of it. If I move this angle again, so this is, you see both these angles are changing. 150.5, 75.25. These are rounded off values. So you might see there is a slight rounding of error here. But otherwise, you can have a good idea. So you see when we move these angles, the angle subtended at the center is always double of the angle subtended at the circumference. So this is our first theorem, that the angle subtended at the center is 2 times the angle subtended at the circumference, right? Moving further. What if this angle subtended at center is made 180 degree? If I change it to 180 degrees, slowly move, what if it becomes 180 degree? So if this angle is 180 degree, obviously upper angle will be 90 degree. So this takes you to your next theorem, that angles made in a semicircle are always 90 degree. You can see theorem here. So angles made in a semicircle are always 90 degree. So the first theorem was angle subtended at the center is 2 times the angle subtended at the circumference, or angle made at the center is 2 times the angle made at the circumference. Number 2, angles made in the semicircle are always 90 degree, right? Moving on to our third theorem. Now, if you see, angle C is an angle that is made in this segment. Chord is AB. So in the upper segment, this is an angle. What if I move this angle? Then what happens? You see, I'm moving it now. Point C is moved. Do you see any change to the angle C? Angle C is not changing. It means all the angles which are made in one segment are same. So this is our third theorem, that angles made in the same segment are always equal, right? So our first theorem was angle made at the center is 2 times the angle made at the circumference. Angle made in a semicircle are always right angles, that is 90 degree. And the third one is angles made in the same segment are always equal, right? Moving on, have a look at this uh, diagram. Now, I would like to draw another line segment here from A. I'll move here and I create another line segment. Now, if you see ADBC, this ADBC is a quadrilateral. This is a very special quadrilateral because all 4 vertices of this quadrilateral lie on a circumference, on the circumference of a circle, right? We call it a cyclic quadrilateral. This is called a cyclic quadrilateral. Now, when angles are made in a cyclic quadrilateral, there is a pattern here. So before we move on to that, let's identify how much is angle D. So I'll go to measurement, measure the angle A, D, and B. Now, if you see, this angle is 124.2 degree, this is 55.82 degree. And of course, when I move these points, all these are dynamic points. When I move, these angles will also change. So let's move and see what is happening here. If you add these two angles, they always add up to 180 degree. These two angles are supplementary angles, right? So this is a cyclic quadrilateral. So this is the property of cyclic quadrilateral, that all 4 vertices of a cyclic quadrilateral lie on a circle, number 1. And number 2 is opposite angles of a cyclic quadrilateral are supplementary, right? So sum of C and D is 180, and sum of A and B will also be 180, because total is 360. So if sum of 2 angles is 180, sum of other 2 will also be 180. So this is your next theorem, that in a cyclic quadrilateral whose all 4 vertices lie on circumference of a circle, opposite angles are always supplementary, right? Now, moving further, now before we move on, I would like to draw a new diagram now, because there are too many lines, too many angles, so you may get confused here. So I'll draw a new diagram. How will I draw? I'll just close this. I'll open a new file. I'll open a new geometry page. I'll go to menu, go to shape, circle, and draw a circle. Now, this time what I'm going to do, again, I'm going to take point and line, go to a segment, and let's draw this segment. Now, at point B, what I'll do is I'll do some construction, and this construction is going to be my okay. So I'm going to at point B, I'm going to draw a tangent now. Tangent, we discussed that tangent is a line that touches a point at one point. So I'll go back to menu, point and line, then I'll go to tangent. Where do I want to draw a tangent? At point B. So I'll just click on point B and I can extend this tangent here. I'll hold it and extend it. Now I see that the tangent is making some angle with the chord. So let's measure what is this angle. So if you go to measurement, angle, and from here if you see, oops, here point B and tangent. So this angle is 49.72 degree. Now you see angle is made out here in this segment. So what is your alternate segment now? The opposite segment. So this bigger segment will be your opposite segment. Now what happens if you draw any angle in this segment? So let's go back to point and line, take a line segment, and let's draw a line here. An angle is made, and let's measure this angle. How much is this angle? So start from A to D to B. So angle ADB. And do you see how much is this angle? 49.72. They are equal. Maybe it's a coincidence. They are equal only in this case. So what do? Let's move these dynamic points and see what happens. So if I move point A, both these angles will change. And even if they change, you see, they remain same. So this is our next theorem, a very important theorem, which is called alternate segment theorem. What is the alternate segment theorem? It says that an angle that is made between a chord and a tangent is always equal to any angle that is made in the alternate segment. So this is how we can explore different angles in a circle. So we stop here today, and in the next video we will see how to work out with these angles and different theorems in questions. Okay, so I hope this video was useful, helpful. If you found it helpful, then consider subscribing it. Please like, subscribe, share, and don't forget to press the bell icon so that you're the first person to get the notification. So take good care until we meet again.